Well, good afternoon, everybody, and firstly, thank you for logging on and joining us for the Dehumidifier CPD seminar on dehumidification and drying. My name is Dave Marshall-George, and I'm the UK and Ireland Sales Director for Condair. And with me is Anthony Hall, who's the Area Sales Manager for Condair. And I'm going to be delivering the presentation today. And in the background, Anthony's going to be dealing with, hopefully, lots of your really difficult questions. Now, we do have the opportunity to handle questions. If you check out the control panel on the GoToWebinar box, you'll see that we have a questions box. So feel free to put any questions, either about dehumidification, humidification, evaporative cooling, or indeed if you have a technical with sight or sound in regard to the presentation, then please pop it in there and we'll do our very best to handle it. The presentation should last around 45 minutes, and then we'll have time for Q&A at the end of the session. So, with no further ado, let's move on to the first slide. So, what we're going to cover today is we're going to look at dehumidifier applications, principles of the psychrometrics, and then we're going to look at products, and then we're going to look at sizing to work out how big dehumidifiers are going to be and the sort of information that we require. And then finally, we'll do a summarization of the presentation and present a comparison between technologies through some of the salient points. So there are literally hundreds of applications that require humidity control. And here's just a few examples where dehumidifiers are usually required. In process applications, the idea is usually to go below the ERH, which is the equilibrium relative humidity of the product, so it dries quicker, which improves production times. For example, some drugs manufacturing processes may require humidity as low as 10% RH, or it could be a food industry application where we're drying meat or producing powdered milk. And what we're doing is we're creating an environment where the relative humidity outside is lower than the vapor pressure is lower than the vapor pressure in the product. So we're drying it out. We're encouraging the moisture to leave the product and drying it out. There are, of course, lots of other applications as well. Storage with museums and archive rooms is very critical. With museums, we've got lots of hygroscopic materials. So hygroscopic materials are going to expand and contract with a change in moisture content. And that expansion and contraction can cause a tremendous amount of damage as different materials and glues act against each other as they expand and contract with a change in moisture content. And very often that expansion and contraction is greater with a change in moisture content than it is with a change in temperature. So it's critical for museums to maintain relative humidity between 45 and 55 typically, which means they're both the humidification and dehumidification application. And one of the worst cases I saw was in a museum in the Midlands where they'd got a 14th century Flemish oil painting, and this thing was oil painted on board, and this thing had expanded and contracted so much that it split from top to bottom, almost enough to get your little finger in there. There was a tremendous amount of damage. In fact, a museum can't accept a travelling exhibition and be covered on its insurances unless they can demonstrate that they've had a stable temperature and a stable relative humidity for 3 months before they accept that exhibition. So it's critical with museums and archive stores, not only to prevent hygroscopic shifting, but also for preservation of artefacts. Energy plants and turbines is quite an interesting one. Here we're dealing with a pipework that contains a fluid that has a fluid temperature that is lower than the dew point of the air around, which means you get cold bridging across the pipework. Because the pipe is being cooled by the fluid, and then you get a surface that in the dew, and that run to cause corrosion, which of course we want to avoid. So by reducing the moisture between 40 and 60% RH. And this is really to make sure that food isn't drawing moisture from the environment, and then it would become in a less saleable condition. So for food preservation. Military hardware or storage, well, actually this could be any goods that are shipped around the world that are typically held in containers. That could be a problem for humidity. If we, let's say, pack a container in the UK and it's 21 degrees C and 50%, and we ship that container to, let's say, the Arctic Circle, we could have a lot of cold bridging happening through the material that the container is manufactured from. So we could have cold surfaces that are below the dew point of the air in the container, and then we can get condensation happening, and then we can get dripping, and we can get moisture dripping on hardware or indeed on goods for sale, which can be spoilt. Swimming pool dehumidification, again, is another important application where we want to avoid condensation, because that's going to lead to rusting and damage to building materials. So dehumidifiers are usually employed in private residential or hotel swimming pools. Larger swimming pools are typically controlled through air handling units. However, all do need a certain amount of air circulation, so typically between 3 and 7 air circulations per hour. And typically, pool rooms should be heated, and it's a very common application, certainly with smaller pools, is that people rely on the pool water to heat the air, which makes it incredibly inefficient because we get a large amount of evaporation from the pool, we get a large amount of condensation, instead of heating the air up to 2 degrees above pool temperature. So we'll come back and look at some pools in a little bit more detail as we go through the presentation. So they're just a fraction of the applications that we get involved in dehumidification. Next, we're going to take a look at the dehumidification principles and the psychrometrics that stand behind the design. So when we start looking at dehumidification, there are two types of technology that we would typically employ, either a condensing dehumidifier or a desiccant dryer, and they are completely different technologies. So firstly, we're going to take a look at condensing dehumidifiers and the principle of operation. So many of you will recognize this schematic of a direct expansion . Oh no. Oh dear.
Yeah, sorry for this, guys. I'm just going to ask Dave to restart this slide when he.
The latent heat.
Hey, Dave, can I stop you there, mate? Dave.
Yeah.
Sorry,
yeah.
sorry to stop you there, mate. Could you start this slide again? You've had a you've lost about 1 minute of sound there, so I do apologise.
I do apologise. Can you hear me now?
Yeah, we can hear you now, Dave. Yeah.
Great. Okay. Well, I will just start from scratch again on this slide. And apologies for those who didn't hear me. This is the first schematic that we're going to look at of a dehumidifier, and this is a direct expansion dehumidifier. And a lot of you will notice or be familiar with the schematic of a direct expansion refrigeration circuit. And we start with a compressor where we compress refrigerant gas to a point where it is going to condense and change from vapor into a liquid at a given temperature. So we've got hot gas condensing into a liquid. We then go through an expansion device. Through the expansion device, we change the pressure of the refrigerant. So the refrigerant will now evaporate at a different temperature. So, and of course, we change the pressure, so we're evaporating at a different temperature. So as we now go into the evaporator, the refrigerant liquid is going to start evaporating and changing its state. Of course, when we change the state of a liquid, we're sucking heat energy out of the air to allow that change of liquid state to happen. So as the refrigerant travels through the evaporator coil, we're going from a liquid, and at the end of this coil, we've taken lots and lots of heat energy out, and we've got hot gas coming back to the compressor, where the whole cycle starts again. So we've got two different temperature surfaces here. We've got a cold surface and we've got a hot surface. A cold surface where the evaporator is sucking heat energy out of the air to change the state of the liquid, and a hot surface where we're changing we're releasing that heat energy. So we've got a hot surface. So how this translates into a condensing dehumidifier is, a good example is to look at your refrigerator at home. If you take your fridge at home and you take the front door off and you take all the food and everything out of the fridge, take all the shelves out, and you blow air straightly into the fridge, the first thing you're going to hit is the evaporator. Now on the back of your fridge is a plate evaporator, but in a dehumidifier it looks like a radiator. It's a heat exchanger. So that air is going to travel over that evaporator, where it's going to first of all cool down and then get even colder as condensation starts to occur on that evaporator coil. So as condensation occurs, of course, we're going below dew point of the air, we're dehumidifying the air. And any condensate, or moisture that we're taking out of the air, gets taken down to a condensation tray and taken away to drain. So then the air, having cooled and dehumidified the air, is now pretty dry and cold. So we then take the back wall of your refrigerator out, and then we're left with air that's going to pass over the condenser coil at the back of your unit. So we're taking air, we're blowing it over the evaporated coil, cooling the air, dehumidifying the air. We've now got dry air, and we're going to now pass air over the condenser coil and blow it out into the space where we have now dry, warm air. Now it's interesting to think, because you may think that as this is a closed cycle system, the DX system, that we're taking some heat out and then we're putting the same amount of heat back in. Well, that is strictly true in the refrigerant, but we have to consider that as we condense water against this evaporator coil, we will be releasing the latent heat of vaporization of the moisture in the air. So you will always get a net heating effect from a condensing dehumidifier. So let's take a look at how that sits against a psychrometric chart. What's psychrometrically happening here? So here we have a traditional psychrometric chart, and I'm sure most of you are familiar with the chart, but I'm just going to run over the basic elements of the chart. First of all, we have the dry bulb temperature starting at -10 and traveling up to 60 degrees C. We have the wet bulb temperature traveling diagonally down the chart. There's 15 degrees C wet bulb, 16, 20, 21, and so on, 25 degrees C wet bulb. We have the specific volume, that's 0.80, 0.81, 0.85, and so on up the chart. And we also have the moisture content, or absolute humidity. So that's shown in kilograms per kilogram of dry air vertically up the psychrometric chart. And then finally, and really importantly for us, is the specific enthalpy in kilojoules per kilogram of dry air. So we have a scale running right the way around the chart that's showing specific enthalpy. And how we read the specific enthalpy is we take a condition, and let's say we are 20 degrees C dry bulb, 14 degrees C wet bulb, 50% relative humidity, 0.007 kilograms per kilogram. If we then draw a line from this scale intersecting our condition to the bottom scale, that is going to give us our specific enthalpy, and more importantly with dehumidification, it's giving us a line of process that we're going to be using when we're dehumidifying. So they're the basic elements that I'm sure you're all familiar with. So looking back at our condensing dehumidifier, what's actually happening? Well, first of all, we're blowing air over that evaporator coil. So you can see as we start to sensibly cool the air, we get a reduction in dry bulb temperature. We see an increase though in relative humidity. There's 50, 60, 70% RH, and up to 100% saturated or dew point. But the evaporator coil is evaporating at something like 6 to 7 degrees C. So it's much colder than this point. So we are going to continue to reduce the temperature. But as the air is already saturated, the moisture is going to fall out in the form of condensation. We'll be doing latent cooling. So we follow the saturation curve down until we reach the moisture content that we want to get to. So we can see first we've done sensible cooling, and then we've done some latent cooling. And then now we're right in between those two coils. So then we pass the air over that condenser, and where we pick up the heat that we took out in the evaporator, but we also get the net gain from the latent heat of vaporization from the moisture that we condensed onto the evaporator coil. So we've condensed that moisture, that vapor from the air, back in from a gas into a liquid, and that's released heat energy into the air. So we have a difference in moisture content, and we have a net heat gain. Now, this is a really useful system for applications that are higher humidity and medium temperatures, because we have a limiting factor here. And that limiting factor is the evaporating temperature of the coil. Now, if we've got an evaporating temperature of 6 and maybe a coil surface temperature of 11, 12 degrees C, then we know that's going to be the minimum moisture content that we can get down to. So if we want something that is below 21 degrees C, 50% RH, then I'm going to struggle to do it with a condensing dehumidifier, because the moisture content is never going to get any lower than that. So it's really important that when we start to look at dehumidification applications, we understand what condition we're trying to achieve. So if you have a high humidity application and medium temperature, so above 21 degrees C, 50% RH, then there's definitely the potential to use a condensing dehumidifier. The next type of dehumidifier that we're going to look at is a desiccant dryer. Now, this is a completely different technology. We don't have any direct expansion refrigeration systems. There's no hot coil, cold coils, nothing like that. Here we're doing something completely different. So let me just go through the diagram. The first thing that's happening here is that we have our process inlet air. So this is air either coming from an external source or it's coming from the space. And we put that air through a fan and we blow it through absorption rotor. And this absorption rotor is going to capture water vapor, and it holds it still, and it releases the heat energy but holds the water vapor. So then we've dried the air, we've captured the water vapor in this rotor, and we take that air back to the space. Brilliant. We've now got dry air. It's warm though, because I've released the sensible heat of vaporization of the liquid back into the space. But now I've got a problem, because my rotor is full of water, or full of vapor, water vapor. So what I do is rotate this disc, this absorption wheel, into a different airflow. And I have air coming from usually an external source through a fan, and then we put it through a heater. And we heat the air up to maybe 125, 130 degrees C. So we've got really warm, really dry air. And we pass that through a section of the rotor. And so these two airflows are separated, and you can see part of the separation vein here. So air is then going to travel over this rotor, and it's going to dry it out because the air is incredibly warm and dry. So we then pick up all of that moisture, and that goes back to external. So we're taking the moisture out of the absorption wheel and dumping it out into the ambient. Now you may say, well, hang on a minute, if I've got 120 degrees C here after this heater, that air is going to be really, really hot. It's going to be warm, but it's not going to be 125 degrees C because we're evaporating water as we go through. So we're adiabatically cooling that air as it goes through that rotor. So we may have 125 degrees C here, but I'm only going to have about 40, 45 degrees C here. So it's not a problem. So what does this look like on a psychrometric chart? So again, we've got our same psychrometric chart. And the first thing that we're doing is we're pushing air through that absorption wheel. Now, we're going to be following our process is the line of enthalpy that we drew from this scale through our condition. As we follow the process and we dehumidify down, we're following this line of enthalpy. So the effect of the process is that I get a decrease in relative humidity. There's 50, 40, 30, 20, and so on. I get a decrease in moisture content, shown in kilograms per kilogram of dry air on the chart. But I also get an increase in temperature because I'm releasing the sensible heat of vaporization. So that heat that's contained in the water vapor is released into the air. But I'm also going to get an additional aspect of heating there, because as the rotor rotates through the different airflows, there will be some residual heat from the warm section of the rotor. So as the rotor passes from the supply air section into the regeneration section and then back into the supply air section, there will be some residual heat. So that has to be considered in our design. So the result is that we get warmer, drier air coming out of the unit. And with regard to the regeneration side, now we mentioned that we'll be taking the temperature up to 120, 125 degrees C, but the psychrometric chart isn't big enough to illustrate that. So just for illustrative purposes, I'm showing here that we are going to sensibly heat that air up. So the air you can see is very, very dry. And then as we heat it up, we're going to adiabatically cool it and release moisture back into the air. But this also gives us some options, because unlike a condensing dehumidifier, a desiccant dehumidifier isn't limited by an evaporation coil, by an evaporator. If I want lower relative humidities, I can achieve it from a desiccant dryer, but I have to go about it a slightly different way. So if let's say I've got an application like a cryogenics lab. So if I've got a cryogenics lab, we're going to have a cryo store that's at maybe -40, and a scientist or researcher has got to get a cryo sample out of that cryo store and put it under a microscope. So if he takes that cryo sample through an ambient air of 21 and 50, you're going to get ice crystals forming on that sample. So we need to dehumidify the air to maybe 21 degrees C, 20% RH. Well, to do that, if I know I'm going to follow my adiabatic process, I have to start with my end condition in mind. So if I'm 21 degrees C and 20% RH, let's say, I'm going to have to start here and follow the line of enthalpy back to a starting condition, which means I'm going to need an air-on condition of about 10.5 degrees C. Well, if I've got an ambient, typical summer design conditions, let's say 28 degrees C dry bulb, 20 degrees C wet bulb, then I need to pre-cool the air to get down to that condition to enable me to then dehumidify down the line of enthalpy to get me to the condition. But then I know I'm going to get a heat gain additionally from the rotor, in which case it's clear I need to both pre-cool and post-cool. So it gets more complicated. It's not just the absorption rotor working on its own. In low humidity applications, we need to be able to think about pre-cooling and post-cooling. So there is certainly more flexibility, but there's also more design involved in desiccant dryers. And it can get even more complicated if you've got an ultra low humidity application such as lithium battery production. Then you're probably going to need 2 or 3 rotors in series as you pre-cool the air, dehumidify, pre-cool again, dehumidify, potentially pre-cool again, and then dehumidify to get you to your absolute moisture content that you require. So it can get quite complicated, and please do come and consult us if you have an application. So here you can see the full psychrometrics that you're following that line of enthalpy down. You've got your initial temperature gain in the latent heat of vaporization that you're releasing. You've got your secondary heat gain from the residual heat from regeneration, and then you've got your process, your wet air, your regeneration air being heated up and dried out. So next we're going to take a look at the products that are involved. And going back to our condensing dehumidifier, here we can see one, that there's not a lot to look at from the outside. They're pretty minimal in power consumption because you're just running a compressor, fan, and small control circuit. And here you can see one. You've got air in coming through a filter, and then air will travel over that evaporator, over the condenser, over the compressor, through the fan, and out into the space. Quick and simple to maintain. It's a filter change and inspection once a year typically. They don't have a refrigerant. Typically, they don't have a refrigerant charge in them large enough to require maintenance by a refrigeration engineer every year. They're easy to install. The ducting is not always required. You can duct from them, but more typically they are just put into the environment where they need to dehumidify, and away they go. All you need to do is provide power and a drain. But of course, we do have a reduced capacity at lower temperatures due to that evaporating temperature of the coil. So we need to be very careful that we don't apply these where we have low humidities or low temperatures. Installation is pretty straightforward. They can just be standalone, and here you can see you've got the air coming into the unit via a filter, over the evaporator, over the condenser and the compressor, and then out into the space. You can have a ducted version, again, where we've got return air going through a grill, a filter, condenser, evaporator, condenser, and then out into the ducts to give you some good distribution. And a swimming pool application, you've got the potential of just having it wall mounted, where you've got your return air coming into the unit, and you've got straight over your 2 coils, your evaporator condenser, and then into the space. Or if you've got a technical area that you can mount the dehumidifier, you can have it rear wall mounted and just have a couple of grills on the return and supply, a short duct to take you into the dehumidifier, and again just over the 2 coils and compressor, and then out into the space. Alternatively, you can have a ceiling mounted unit and also have the opportunity to run a heat exchanger, so you can use some of that latent heat of vaporization to put into your swimming pool water. So it just saves it, instead of putting it there, you can put it into the water. Makes it a little bit more efficient. Next, we'll have a look at desiccant dryers. So this is a pretty good example of a desiccant dryer. You can see we mentioned we've got 2 different airflows. You've got your supply air here. Supply air is always going to be bigger than the return air. And then you've got the power and controls. You have got a higher power consumption with these units because we've got to regenerate that wheel. And typically that's done through an electric heater. There are other options, but typically electric. They're simple and easy to maintain. Again, full filter changes, inspections. We can expect the rotor to last a good 10 to 12, 13 years without any trouble at all. They are a ducted installation. Again, we've got 2 airflows here, which we can't mix. So we've got to duct the supply air from the space or from the air handling unit through the unit back to the space, and then we've got to duct that regeneration air, ideally from outside, through the unit, and then dumping that wet moisture again outside. of course, we can operate to a very low dew point. So we can work with much colder temperatures. Now it does raise a question as well. We can operate these units down to -30 degrees C, which raises a question that, well, why don't we experience freezing in there? We've got water in there and we can operate it down to -30. But what's actually happening inside that rotor is that we're capturing the water vapor in its vaporous state, and we're just holding it still. So we're releasing the heat energy by holding that water vapor still, but it's not turning into a liquid. So we won't see freezing as we get down to those lower temperatures. So the water vapor is then re-energized as we regenerate the wheel and we apply that hot air to it. And then the energy is taken back into the liquid, into the vapor, and it's released into the air. So we don't have water in its liquid state inside the desiccant dryer. We mentioned we've got electric, but you can have gas or steam regeneration if that's available to you. So if you're in a pharmaceutical application, you could well have a live steam supply that could be used to put in the heat exchanger. Vast majority of units are using electricity to produce steam. And of course, we mentioned that we can pre and post cool. And indeed, to get down to those lower moisture contents, we are going to have to pre-cool to get down to the point where we can achieve maybe 5 grams of moisture removal. And then, of course, we may need to post-cool to offset the latent heat of vaporization and the residual heat that we're going to get from the rotor. So here's a schematic of what the unit is going to look like. First of all, we have our process air coming in, so either coming from an air handling unit or coming from our space. We'll have a damper there so we can control that airflow. We have a filter and then a fan, and then we pass that air through that absorption rotor that again is rotating slowly. The water vapor is captured in that absorption rotor, and then air is taken out, and we've got dry, warm air that we take out to the space. And again, we may have to post-cool that air. And on the other side, our reactivation air is coming from the outside. Again, we have a damper, we have a filter and a fan, and then we have our heater. Again, we're going to take that air up to maybe 120, 125 degrees C and warm up that section of the rotor as the rotor passes through that airstream. So that captured vapor is then released into the wet air, and we have wet air. And again, we're going to be 80, 90% R rate, something like that, but maybe 40, 45 degrees C. So you can see how critical it is that those two airflows don't mix. So we've looked at applications, principles, psychrometrics products. Let's take a look at sizing. How do you work out how big one of these things is going to be? Okay, we're going to need some design data. The first aspect of the design data that we need is the external load data. The first thing we want to know is what are the outside air conditions that we're going to be experiencing where we site this dehumidifier. So typically that will be the most moist conditions that you're going to see. So in the northern hemisphere, that will be a summer condition that we'll be working to. So we'll look at the degree C and the percentage RH that we're going to experience. Then we look at the room set point. What condition are we trying to achieve in our space? And again, this will dictate the type of technology that we would apply. We then look at what is the absolute moisture difference between these two conditions. And we'll take that from the psychrometric chart or from the tables in the CIBSE guide. We then want to know how much air are we trying to dehumidify? So we'll look at the air volume or the room volume if we don't have any mechanical ventilation. And then we'll take the specific volume of the air. So our external load calculation is our moisture difference in kilograms per kilogram of dry air multiplied by our air volume, multiplied by 3600, because we want litres or kilos an hour, and we've gone from meters cubed per second, and we divide that by the specific volume. So that's okay, that gives us an external load figure, but it's not the only part of the story. We also need to know what is our internal load for the dehumidifier, and that's going to be made up of a number of figures. Firstly, the number of occupants. ASHRAE gives us some guidance here as to the moisture that we can expect to see from occupants. So an occupant working at a low intensity, we should give off 35 grams per person per hour. Somebody working at a medium intensity gives off 110 grams per person per hour. Of course, these are lines in the sand and it will vary from person to person, but these are typical values. And a person working at a high intensity, something like an application such as a gymnasium, you'd expect 185 grams per person per hour. So it makes an awful lot of difference to the load calculation depending on what the person is doing. Then I need to consider any additional moisture loads. Now that could be an open water surface, or it could be moisture released from a product by, if we're drying and curing meat, for example. So our total load will be our external load plus our internal load. Swimming pools are slightly different. We do need to know the room volume, so how much air are we trying to dehumidify. We need to know the pool surface area, so we can calculate the evaporation rate that we are going to get from that pool surface. To do that, as well, we're going to need the water temperature and the room temperature. And again, I mentioned earlier in the presentation, it makes a huge difference. You've got a pool temperature of 35 degrees C and an air temperature of 15 degrees C, you'll get a huge amount of evaporation coming off that pool. And you need a huge dehumidifier to cope with it. As opposed to keeping the air temperature a couple of degrees above the pool temperature, will dramatically reduce the evaporation that takes place from that pool, and again make your facility much more efficient. So we need to know the room humidity set point as well, and also the daily hours of operation and the type of usage. So if it's just a private pool, that will have a utilization factor. If it's a training facility or perhaps a spa, then that will have a different level of usage, and there will be different factors in there that calculate that evaporation unit. We'll also need to know whether the pool is covered or not. Air circulation rates should be between 3 to 7 total air changes per hour. So there is some additional information required for swimming pools. So now we can do a comparison between the different technologies, and a really good graph that illustrates the difference between the technologies is this one, and it's showing different inside air humidities going up from 20 to 100%, and air temperatures going from -10 to 35. And you can see that actually if you are above 20 degrees C and 50% RH, you're into the type of application where you can use a condensing dehumidifier. Remember, we're limited with a condensing dehumidifier by the evaporating temperature of that coil. We're never going to get lower than 20 degrees, 50% RH typically. As soon as we do travel below than that, our efficiency falls down really, really quickly. But if we've got a lower temperature or a lower humidity that we're trying to achieve, then that falls into the desiccant dryer applications. So a pretty good rule of thumb, anything over 20 degrees, 50% as a room set point, you would consider a condensing dehumidifier. Anything below that, always a desiccant dryer. So to look at the comparison between the technologies, well, we've got our two technologies here. We've got a condensing dehumidifier and our desiccant dryer. The dehumidification principle with a condensing dehumidifier is that direct expansion refrigeration circuit that we looked at in some detail. Whereas a desiccant dryer is that absorption wheel that is going to capture water vapor and then release it in a hot air stream. Electrical power consumption, well, it's pretty low for a condensing dehumidifier. We're running a compressor and a fan and some controls, but you know, it's not too bad at all. Whereas with a desiccant dryer, it is going to be higher and constant because we're running that heater for the reactivation air, so that regeneration air. Heat emissions to room, it's slight to moderate with a condensing dehumidifier. Again, we've got that small heat gain from the latent heat of vaporization, but it's going to be higher with a desiccant wheel because, again, it's that adiabatic process. We see the release of the latent heat of vaporization plus the additional heat from the rotor as it rotates. No ducting required for a condensing dehumidifier, but we always need ducting from a desiccant dryer because, of course, we can't allow those two airflows to mix. Achievable relative humidity, yeah, 50% RH from a condensing, but down to 1% RH from a desiccant dryer. Operating temperature range, 15 to 36 for a condensing dehumidifier, absolutely fine. And again, a desiccant dryer, -30 to +40. Remember, we're not allowing liquid water to reach its liquid phase inside that desiccant dryer. We're capturing water vapor. So we don't have an issue with freezing. Installation type, it's mobile or stationary with a condenser. It's quite common to use it for disaster recovery, that sort of application. But the desiccant dryer, usually stationary because we're ducting to it. We have a higher air circulation rate with a condensing dehumidifier, and that's just down to the thermodynamics of the heat exchangers. Well, lower air circulation rate with a desiccant dryer as we allow the air to travel, spend more time in contact with that absorption wheel. We get higher dehumidification capacities at higher temperatures with the condensing unit, and we've talked in some detail about why that would be. You also get that high dehumidification capacity from the desiccant wheel, but as soon as that temperature starts to fall, with a condensing unit, it will start to fall away, whereas with a desiccant, it will remain high to constant. Power consumption, the kilowatts per kilogram of condensate, 0.5 to 1.5 in a condensing dehumidifier, and not a lot more for a desiccant dryer, so there's not a huge amount in it. So the thing that we've got to remember is with dehumidification, what are we trying to achieve? What condition are we trying to achieve? That is going to dictate the type of technology and the considerations that you have to make when choosing a dehumidifier. So we design, manufacture, commission, service, site surveys, risk assessments, anything from moving a box to an end user or doing a full turnkey supply package. I'd also like to draw your attention to the downloads, while I still have you all, on the control panel. There is a Condair dehumidifier brochure. There is a dehumidification and drying, the psychrometric copy of the presentation, and an electronic copy of the psychrometric chart. So please download those. And of course, if you want any further information on any of the products, they're all available at condair.co.uk. And of course, if you have any questions that we don't get to in a minute, then of course you can send them to me directly. So that's the end of the presentation. Now I'd like to open up and see if we have any questions from the audience.
Hi Dave, yes, we have loads of a myriad of questions. Thanks guys for all the questions, and thank you all for the comments regarding the audio. Do apologise about the audio. I think we just had a few issues with the internet earlier on, so hopefully it seemed to go all right my end once we got that sorted out. So thanks everybody for pointing that out. Lots of questions, Dave. What we will do, apologies if I don't get through everybody's because we've got a lot of questions here. So I'm just going to pick out some pertinent ones, but rest assured, those that we don't answer today, we will get back to them. So firstly, good question is, do condensing humidifiers fall under any F-gas regulations if using refrigerant?
Yeah, well, I mean, obviously they have to be worked on by an F-gas engineer, but critically, they don't have a refrigerant charge in them that's large enough to require maintenance and service by an F-gas engineer every year.
Okay, bro. Next question. Can you explain the rule for working out residual heat on the rotor, please, for desiccant units?
It's incredibly complicated, if I'm honest with you. Typically, you will see 1.5 degrees C per gram heat increase per gram of dehumidification from a desiccant dryer. And that includes the heat transfer from the rotor. But it does vary with different fan motors and different rotor thicknesses, and so it varies from machine to machine. So I would always suggest that you come to us for a selection, and then we will run it through the software that will calculate with the relevant fans, regeneration heaters, regeneration heat temperature, what the heat gain is going to be. So we will advise as to what size, how many kilowatts of post-cooling that you're going to require.
Another question here is, does the desiccant wheel capture moisture, and how does it do it?
Yeah, that's a great question. And we mentioned that a desiccant wheel isn't condensing the moisture into a liquid. It's like a surface that has an incredibly massive surface area. I mean, absolutely enormous surface area with so many small pores and holes in it that it captures water vapor. So water vapor, when it's in its vaporous state, contains energy, and that is what is keeping it in that state. But when that water vapor hits the absorption wheel, then it's caught in one of these tiny pores, and that holds that vapor molecule still, and it releases the heat energy that is ordinarily moving that molecule around. So that's where we're getting the latent heat of vaporization, but we're holding that gas or that vapor in its gaseous state. We're not allowing it to change into a liquid. So that allows us to work at those lower temperatures because we're not because it's not going to freeze. So then when the rotor rotates into the hot airflow, it's then regenerated with that heat energy and is released into the airflow as we dry that rotor out.
Okay, we'll do two more questions, so I'm conscious of time, everybody. First one being, do you always need to pre-cool the process air before it enters a desiccant dehumidifier?
Yeah, that's a good question. It very much depends on what you're trying to achieve. So if you're trying to achieve a lower condition, then pretty much we know that we're going to be following that that line of enthalpy down the chart. So we need to look back to say, okay, can I get to the condition that I want? Typically, bear in mind that a desiccant unit will only give you 5 grams moisture removal. So are you going to be able to achieve your 5 grams moisture removal at your supply temperature? So if you've got an air on temperature of 21 degrees C, or let's say 28 degrees C20, are you going to get to the condition that you want to get to by just removing 5 grams? If you can't do that, then we've got to pre-cool to do some of that dehumidification in a cooling coil before we hit the desiccant wheel. So that defines whether we need to pre-cool the air, depending on the condition that you want to achieve.
Brilliant, Dave, thank you. And then last question, last but not least, another great question. Is there a certain air leakage the room has to have for the room to work efficiently?
That's an interesting question. Air leakage. No, I mean, air leakage we would consider as part of, because if air leaks, then we've got an infiltration rate. And the infiltration rate will be added to our load calculation. So we would want to know really what leakage rate you would expect, and we would add that into the duty calc of the dehumidifier. So not especially critical, but we do need to know what you would expect the infiltration rate to be if you're leaking air.
Okay, like I said, I have loads more questions here, but I'm very conscious of time. I do promise we will come back to everybody's questions, but over to you, Dave. Thank you very much.
Great. Well, again, thank you everybody for bearing with us. I know everybody's very screen weary these days, so I really appreciate it. Please make use of the handouts and the downloads. And again, if you do have an application, please feel free to contact us for humidifiers, dehumidifiers, and evaporative cooling. And you'll get all the product information at condair.co.uk. And once again, thank you. You will get a CPD certificate emailed to you if you use your original login. And again, if you have any applications, please feel free to get in touch.
Thanks, guys.
Brilliant. Thank you, everybody. Have a great day. Really appreciate you joining us for this.
Cheers. Bye-bye.